Welcome back to Physical Science 101. This is the fourth and final lesson of Unit 2. I believe it'll be a rather short lesson, and it will also have a fun demonstration for you. What we're going to talk about in this final lesson is a new idea called momentum. Momentum, we define momentum to be the product of an object's mass and its velocity. So momentum equals mass times velocity. Since velocity is a vector, momentum is also a vector. That means that momentum has both amount and direction. The amount of momentum is the object's mass times the object's speed, and the direction of momentum is the direction of the object's velocity. So momentum is a vector, has amount and direction. The amount of momentum is the object's mass times its speed, and the direction of momentum is the direction of the object's velocity. Now, to see the significance of momentum, we're going to go back to Newton's second law. Okay, I'm going to write Newton's second law as the unbalanced force divided by the mass is equal to the object's acceleration. So that's Newton's second law, where I've just reversed the left and right-hand sides of it. Next, I'm going to write acceleration as change in speed over change in time. So force over mass is equal to, and in the place of acceleration, I'm going to write change in speed over time. Okay, now I'm going to multiply both sides by mass, and I'm going to multiply both sides by time. So mass times time, and mass times time. Okay, now what happens on this side, mass cancels out, and on this side, time cancels out. So I've canceled out my mass and my time, and what am I left with? I'm left with force times time is equal to mass times change in speed. Okay, so this is just Newton's second law reworked to give us mass times change in speed. So we have a new idea, and the new idea is that force times time is equal to mass times the change in speed, which would be the change in momentum. Okay, so the idea here is when we apply a force to an object over a certain time, we're going to change that object's momentum. So applying a force over a time changes that object's momentum. Now, let's bring in Newton's third law. When one object exerts a force on another object, each object feels the same amount of force, but in opposite directions. That's Newton's third law. Okay. Now, if an object exerts a force on another object, we know that they're going to feel the force for the same amount of time. Because if one object pushes on another object, then that object pushes back for the same amount of time. So, force times time is the same for both objects. So for both objects, I can write that force times time is equal to the mass of object 1 times the change in speed of object 1, because force is equal to change in momentum. But the second object also feels the same force for the same time. So so that's also equal to the mass of object 2 times the change in object 2's speed. So what we see is whenever two objects interact, mass 1 times the change in speed 1 equals mass 2 times the change in speed 2. And why is that? It's because force times time changes momentum, and both objects feel the same force for the same time. So the two interacting objects will feel the same change in momentum. The amount of the change in momentum will be the same. The directions will be opposite. And this equation here is important enough that it gets a name. This is called conservation of momentum, meaning that the change in momentum is the same for both objects, but in opposite directions. Okay, let's get to that demonstration that I promised you. Okay, here we are again with the skateboard and the platform, and this time we're going to talk about conservation of momentum. We're going to have two objects that are interacting. The two objects that are interacting are myself and the skateboard. That's one object. So when I stand on the skateboard and I become a single object. The other object is the platform. So I'm going to push on the platform, as I did before, and then because the skateboard and I are interacting with the platform, when I push on the platform for a certain time, the platform pushes back on me with an equal and opposite force for the same time. So we both get the same change in momentum. Since we start with zero momentum, we'll both wind up with the same momentum, equal but in opposite directions. Okay, I have a mass of about 80 kilograms. The platform has a mass of about 5 kilograms. So I have a much larger mass than the platform. So my mass is large, therefore my momentum is going to be small, my velocity is going to be small. Large mass, small velocity. The platform will have small mass, large velocity. So let me demonstrate that. Okay, here we go. Okay, the platform has a large mass. I have a small, almost non-existent mass. Okay, so mass times velocity is the same for both of us. The platform has a small mass, large velocity. I have a large mass, small velocity. Now let's even the scales a little bit. I'm going to get this 40-pound, 20-kilogram bucket of sand here. So now the platform has a mass of about 25 kilograms. I have a mass of about 80 kilograms. So I will still have a much smaller velocity than the platform, but it won't be as different. The difference won't be as great as it was before. So now I should get a little more velocity out of this deal. Okay? So let me try that. So here we go. I'll push off. I got a little bit more velocity out of that. So mass times velocity is the same. We brought the masses closer, so we brought the velocities closer. The platform still has the larger velocity, and I still have the smaller velocity, but since we've brought the masses a little bit closer to even, we've brought the velocities a little bit closer to even. Okay, let's get another bucket of sand. Okay. So now that's 40 kilograms, 45 total. I have 80. So the platform has about half of my mass, so it should have about twice my velocity. So now, whatever velocity the platform has, I'll have about half of that. So I should be moving forward a little bit better. But my mass times my velocity equals that mass times that velocity. That's a smaller mass, larger velocity, larger mass, smaller velocity. But now we're bringing the masses closer to each other, so the velocity should be a little bit closer. So I should be getting a little bit more forward velocity here. Okay, here we go. Oh yeah, little bit more. Little bit more. Okay, I have one more bucket of sand. Let's bring that bucket of sand in. Now we're getting closer to having the same mass, So we should be getting closer to having the same velocity. Okay, here we go. I should get more forward velocity out of this. That's getting better, getting better, getting better. Now, if I really want to have a good forward velocity, I'll push off of something with a lot more mass, that being the Earth. The Earth has an enormous mass. So the Earth will have an enormous mass and a tiny velocity. I'll have a small mass and a large velocity, at least compared to the Earth. So here we go. Push off on the Earth, and there we go. Okay, so there you go. That is conservation of momentum. When two objects interact, the mass times velocity is the same for both. A small mass will have a large velocity. A large mass will have a small velocity. Okay, I hope that was fun for you. It was fun for me. Before we go, I have one more question to ask you, and that is, a 0.02 kilogram bullet is fired with a speed of 600 meters per second from a 4 kilogram rifle. And the question is simply, what is the recoil speed of the rifle? Okay, draw a diagram. Get everything that you're given into your diagram, into your model. Think of the principle to apply. The principle will give you an equation, and then you can work through the equation. Okay, pause, do that, and when you're ready for me to lead you through the exercise, unpause. Okay, let's draw a diagram. Here's the rifle, and I will draw the bullet in the rifle. So there's the bullet in the rifle before firing. Okay, and I will write mass of the rifle is equal to 4 kilograms. Mass of the bullet is 0.02 kilograms. And initially, V bullet is equal to 0 and V rifle is equal to 0. So that's our start, that's how things start. And then afterwards, the bullet goes out, and we have V bullet is equal to 600 meters per second. And V rifle, we don't know. Okay, I think that's everything. So now we'll think about what the principle to apply here is. Well, we have two objects interacting, changing their speed, they're changing their momentum. So let's try conservation of momentum. Conservation of momentum would be mass 1, change in speed 1, is equal to mass 2, change in speed 2. Okay, well, let's let mass 1 be the rifle, so that'd be mass rifle. And the change in the rifle speed, it goes from 0 to V rifle. So the change in the speed is just whatever that V rifle is. And object 2 is the bullet, so that would be mass of the bullet. And once again, the bullet speed goes from 0 to V bullet, so the change is just V bullet. So our conservation momentum says mass rifle times V rifle is equal to mass of bullet times V bullet. And we want to know V rifles, so I will divide by mass of the rifle, divide both sides by mass of the rifle. Mass of the rifle cancels out, and I have V rifle is mass of the bullet over mass of the rifle times the speed of the bullet. And now we can put in our data for the specific situation. Speed of the rifle is mass of the bullet. Mass of the bullet is 0.02 kilograms divided by mass of the rifle, 4 kilograms, times V bullet, 600 meters per second. Okay, I'll do my units first. Kilograms, cancel out kilograms, and I'm just left with meters per second. Now I will do my numbers. I have 0.02. That's 0.02 times 600 divided by 4. And that is 3.00 meters per second. So the bullet has a small mass but a very high speed. The rifle has a large mass and small speed. And specifically, the bullet has a speed of 600 meters per second. The rifle has a speed of 3 meters per second. And that is an application of conservation of momentum. Okay, that's the end of Unit 2. We'll start next time with Unit 3, which is going to be on the subject of energy. Until then, think science.